Hello there and welcome. My name is Michael Fudge, and this is our dimensional modeling lecture from IST722 Data Warehousing. One important note before I begin this lesson is that the PowerPoint slides that you can download from our learning management system have a bunch of quizzes with answers on them, and they're a way of kind of checking yourself as you go through the PowerPoint lecture. I've left those out of the video, one, to save on a little bit of time, and two, because it doesn't make sense for me to ask a bunch of questions that no one's going to answer. So one thing I encourage you to do is look at the PowerPoint slides in the learning management system and quiz yourself a little bit on your knowledge of a lot of the terminology that we'll be covering today. Okay, thank you. Let's get started. So today's objective is to define and explain dimensional modeling. We're going to cover a lot of concepts today. You might have to watch this video more than once to really hone in and get a fix on what's going on here. It's important to recognize there's going to be a lot of new concepts, and you'll need to become intimate with these concepts in order to succeed in the course. As you recall, the Kimball Lifecycle is a reference architecture for project management associated with a data warehousing effort. Right now, we're in the dimensional modeling portion, which is in the middle layer where we do dimensional modeling, physical design, and then ETL, design and development. One thing I want to do is define dimensional modeling. A dimensional model is a logical design technique that we use to structure our data with the following purposes. One, we want it to be intuitive, that is, easy for our business users to understand. And two, we want it to be fast. Excellent query performance. If you've ever queried a transactional database, you know that you can build a lot of joins into your tables before you actually get to the result you want. And then sometimes the data isn't even structured in a manner conducive to getting the results that you need. So one of the key reasons for the discipline of data warehousing is that we can restructure our data out of our transactional systems in a mean that is supportive to querying and analytics. This is the key goal of dimensional modeling, to reshape our data into a form that's easier for our users. You probably recall the corporate information factory. This is Inman's view of the physical components required to implement an enterprise data warehouse solution. And what I've done for you now is I've taken red boxes and I've highlighted the areas in the corporate information factory that contain relational models. So everything that you see with a red box has normalized data. This has operational data or transactional data associated with real business systems. And then the green boxes represent the transformation of that operational data into a dimensional model. So in the decision support applications and in the data mining applications and in the enterprise data warehouse and data marts, these are all where we use our dimensional models. So it kind of gives you a feel for any given business problem. Maybe it's graduate applications at a college, for example. That business problem has a corporate application, a place where students can apply and track their applications, but then we might also take that data, transform it, put it in some kind of data mart. That same data is represented differently by a different model so that it's easier to query. So this kind of helps put it all together. One thing you'll notice that in the middle of the diagram there's no box around ETL, because ETL is really the process that converts our operational data into dimensional data. That's one of the key goals of ETL. One of the other things we do with ETL obviously is copy our data out of our operational databases and into our ODS, our operational data store. Let's start with the components of the dimensional model. First, we have the fact table. This is merely a relational database table of quantifiable performance measurements. We call these measurements facts. So a fact can be something like a sales amount, or how many days it takes to ship, or the number of things that we have on hand. A dimension table adds our context to our fact. So these are kind of the categories associated with the fact, like dates and times or locations or customers and products. Then we have attributes, which are characteristics of our dimension. So these give us some detail to our dimension, like the name of the product, or the category of the product, or which department sells the product. And then all of this combines together in a star schema. And a star schema is just a way of representing this with a relational structure where we have our facts, and then out from our facts we have our dimensions in a many-to-one relationship, if you will, and it ends up looking like a star. So that's why we call it a star schema. Here's how I like to think about dimensional modeling. I want you to, for a minute, think of yourself trying to solve a business problem. So if you were a business manager, you might ask a question like, how many sneakers did we sell last week? So something as simple as that can be broken down into this concept of facts and attributes and dimensions. So let me show you. So how many, that's our fact, that's a quantity. Sneakers, that's a product type, which is an attribute of the product dimension. It's a very specific product type. And then did we sell? That's the business process that we're trying to capture. So the data mart would be the sales data mart. Last week, that's a duration of time. That's another dimension. So as you can see, any type of query that you might ask of your data can be broken out into this same format. And when you think about the types of queries that people need, you can easily extract from their queries your dimensions that you might need and your facts and the business process behind those. And this is how I like to dimensional model. I start with my users, I try to figure out what they're doing and how they're doing it, and from there I build out my dimensions and facts. Here's an example of a star schema. So a star schema has a fact table in the middle, and then inside the fact table are the facts themselves. These are always some kind of numeric or quantifiable value. Then the fact table has a bunch of foreign keys that connect back to the outer tables in the star schema. These represent the dimensions or categories of data. So this particular sales schema could be queried by customer, location, time, and product. Those are the four different dimensions that we have in this in this sales schema with a fact table. There are three kinds of facts that we would have in any fact table. One of them is additive, and the additive fact is the most common kind of fact. It's the goal that we want to achieve all facts to be additive, which means they can be summed across all your dimensions. Again, this is the most useful kind of fact. So something like quantity of products sold or number of hours billed to a client, those are additive facts. You can roll that number of hours billed up by the customer. You can roll that number of hours up by the technician or project person who worked on the project. You can also roll that up by billing category or billing code. You can also roll it up by time. It's very additive. Semi-additive facts cannot be summed across all the dimensions. Usually the semi-additive fact does not work across time as the dimension. So for example, you might have something like an account balance that you get every month from your credit card bill. That number changes every month. You can certainly it could be additive across other dimensions, but it doesn't make sense to add that up over time, because the balance from one month could be like $50, and then the balance from the next month could be $100. But to say the balance across 2 months is $150 doesn't make any sense. It might make more sense to average that value across time. So it's important to recognize with each of your facts in your fact table, is that fact an additive or a semi-additive, or maybe it's non-additive. If you find a non-additive fact, that should raise a flag, and you should say, wait a minute, this fact is not quantifiable at all by any dimensions, and therefore it probably doesn't belong in my fact table. It's probably a dimension instead. So for example, the square footage of a building, doesn't make sense to add that up in a certain situation, so it wouldn't be an additive fact. So it's probably just a characteristic of a building that we want to capture and be able to sort or search or filter by. And here's my good fact detecting rule I like to apply. When you have a candidate that you think would be a fact for your fact table, the first thing you should ask is it completely additive? Does it add up across all my potential dimensions? If it does, then it's a fact. Do I use it for filtering or labeling If that's the case, then it's not a fact. For example, the height of a basketball player, while you could measure that in centimeters or inches, that is not additive. That is really used as a way to filter or categorize that player. So you might have a player that is higher than 7 feet, and you want to know what is the average points per game of NBA basketball players who are higher than 7 feet. 7 feet is not a fact, it is a dimension. It is a way we use to categorize another measurement. If that potential item is used in a calculation, then it should be treated as a fact. For example, if we take hourly wage and we use that to calculate how much we pay you each week, then hourly wage has to be used as part of that fact, even though it doesn't make sense to take hourly wage and add it up over time. Okay. It makes sense to add up weekly pay over time. Let's talk about the design of our fact table. Now, what I'm talking about when I say design of our fact table, I'm referring to how we would create this table in a relational database and set primary keys. So here's the rules of thumb. Your primary key in your fact table should have as few columns as possible, and it should not use surrogate keys. Okay. Generally, it's made up of foreign keys and what are called degenerate dimensions. We're going to learn about degenerate dimensions in a little bit. But in essence, a degenerate dimension, while it's very difficult for me to say, obviously, is a piece of data that goes in your fact table that helps you reference how that fact got there. Like, for example, it might be an order number, or it might be a transaction ID or something like that. It's definitely not something that we add up, but it's something that we can use to reference how the fact got there. Referential integrity is a must, and referential integrity, if you do not remember, is a rule that we put in our relational model that says you can't add a value in a particular column because it's constrained by the list of primary keys in another table. And this is so important because what you don't want to have happen is you don't want to add facts that don't refer to dimensions. Okay, and that's exactly what could happen if you don't have foreign keys set. You want to avoid nulls in your foreign keys and instead use flags to represent the conditions. For example, if you're trying to do a frequent shopper dimensional model for a grocery store and you decide, okay, well, I might have a frequent shopper card or I might not have a frequent shopper card, what you don't want to do is use null. What you'd rather do when they don't have a frequent shopper card is put in a value like no shopper card. That way, when someone goes to look or query the dimensional model, they don't have to make an assumption about what it means when it's null. They just see two values, shopper card, no shopper card. Or you might have three values, shopper card, no shopper card on the day they bought this, or didn't sign up for shopper card program, right? That way you can be more granular in your dimensions. Finally, what each row in that fact table means is very important, and it's something that you have to think about and consider when you first create your dimensional model. And this is usually captured by the underlying business process. We'll talk about this more in a future slide. Let's talk about dimensions for a bit. Dimensions provide the context for our facts. We can easily identify the dimensions in the problem that we're trying to solve. When our users say the word by or for, that usually what comes after that word is typically a dimension. For example, someone might say, I need to see the total account receivables for the IT department by month. So IT department is a specific piece of data in a dimension, maybe that covers all the departments. And then month is a specific attribute in a date dimension. Dimensions have attributes which describe and categorize their values, right? So it's important that the dimension is filled with different attributes that have meaning. And these attributes that are in these dimensions help us to solve the problem. So for example, if it's a student, we might want to find out the average GPA by major, or the average GPA by year, or maybe the average GPA by gender or dormitory. Those would all be attributes of a student dimension so that we can further categorize the facts that we've identified. Attributes are useful because they help us filter and roll up or aggregate those facts to the grain level that we need to answer the question, whether it's again by month or by year or by quarter or by day or by hour across the date dimension. Okay, some rules when you design a relational table that has a dimension in it. You want to use as descriptive column names as possible. Okay, you don't want to call it shop club card. Just spell it right out, shoppers club cards. Be as descriptive as possible because these columns are going to be used or typically read by end users or business users, and they may not understand what the cryptic meanings are all about. So it's important to be as descriptive as possible. Make sure the fact table, make sure the dimension table has no null values, right? So in any row where you have a particular dimension value, you want to make sure that the attributes don't have nulls. Use flags instead. There should be one value per row, so you shouldn't have one row that has a student in it, and then the next row has the same student in it. That doesn't make any sense, especially in a dimension called students. It might make sense in a different dimension. And you always want to make sure that your data in your dimension is as clean and consistent as possible. There's no typos. One of the things that'll really blow up your dimensional model is typos. For example, you have a list of fruit, and you have apples, oranges, and cherries, and then someone spells cherries two different ways. That's going to throw off your roll-ups as you try to group that data by the type of fruit. You're going to see cherries in there twice. And last but not least, the primary key in a dimension table is always a surrogate key. There's only one situation where that's not. We'll talk about that in a little bit. But generally speaking, you want a auto-generated numeric value, sequential numeric value to be used for your dimension table's key. Now that doesn't mean that your dimension table does not have what's called a natural key, right? You should be able to look through the set of data in any dimension and say, this is what a human being would look at this data and say, that is unique. So for example, if you were doing an e-commerce data mart and you had a customer's dimension, you might have an email address that you use to uniquely identify each of your customers, or maybe it's the log-on to their site. So that value would be the natural key, but you certainly would not use that natural key as the primary key in the table. That is a no-no. And there's a few reasons for that, but the biggest reason for that is that those values can change over time. And one of the goals of a dimensional model is to collect data over time so that it's time invariant. And if you change primary keys, you're going to lose that time invariance. So it's extremely important that you don't use natural keys. Don't even think about it when you make a dimension. Just use a surrogate key. In Oracle, you'd use a sequence. In Microsoft SQL Server, you use what's called int identity. This is also going to help the performance of your star schema because you have integers as your primary key and integers as your foreign key. Integers are extremely easy to key on in a relational model, so it's going to make your performance much better. And because of the fact that those integers are sequential, the data will be inserted in a manner that's conducive to growing the file in the right way. It's not going to be as fragmented. The data in the physical file of the tables, it won't be fragmented, and that will greatly speed up your queries as well. So let's talk a little bit about what a conformed dimension is. So a conformed dimension is just a concept that we use that says, I have one data mart, and it has a dimension. Let's just pick on a particular dimension called date. And then I have another data mart, and that data mart has a dimension called date. So why would I make two physical tables called date that have exactly the same dimensional data in it when I can just reuse that dimension across those individual data marts? So that's the idea behind a conformed dimension. Here's an example of a conformed dimension. This is a subset conformed dimension. So we have one data mart at the top where we have sales, and that sales has a product dimension. And then there's another data mart at the bottom called forecasts, and that has a brand dimension. And the brand dimension is actually a subset of the product dimension. So this is an example of a conformed dimension. You would actually generate that brand dimension from the source data in the product dimension. As we'll learn as we go on in the class, you can do this in a couple of ways depending on the data size of the dimension. You can make a view that generates the brand dimension, or you can use the ETL process to create a separate table from that. But the important thing to recognize is that the data is sourced from the product dimension, and therefore we don't ever have to worry about the data getting out of sync, right? And that's really what we're trying to avoid with a conformed dimension. It's okay to have 5 date tables in your enterprise data warehouse. What's not okay is to have them have different values in it. Okay, and that's the purpose of a conformed dimension. Is it's part of the master data management plan where we have one way to get to that data and then use that authoritative source to populate all the other things so that everybody is on the same page and using the same sets of data in their dimensional models. Let's talk about the most common conformed dimension out there, known as the date and time dimensions. Generally speaking, as an implementation standpoint, you might make a date dimension, and then you might also make a time dimension, but you generally would not make a date and time dimension as one thing. You make those separate. So the date dimension is a conformed dimension. We usually generate the date dimension programmatically using it during the ETL process, or we just fire it all up in a spreadsheet, make it in a spreadsheet, and then import it. But the bottom line here is that the date dimension has meaningful values in it that are usually calculated or derived, and they're there to just kind of grok more useful information from our underlying data. So for example, I have a date dimension here that I'm showing you a screenshot of. In the fact table, we might have, like, maybe we have a fact table of orders, and I have order date in that orders table. I would store the date key in the fact table as the foreign key. See this? So 2013-720 would be the date key, for example. Now this is the one exception to the rule where when you make a date dimension, you don't want to use a surrogate key. You want to generate a date key with year, month, day. You can certainly use a surrogate key. There's no rule that says you can't. It's just it becomes a little more readable to do it this way when you look at the fact table without joining it back to the dimension. But here's what I'm trying to get at is that 7/20/2013 is on a Saturday, right? So I have to figure that out somehow. I just used Excel to do that because Excel has all sorts of great functions to do that. But my point is that for that date, that's always going to be a Saturday, right? The next date after that is always going to be a Sunday. And we want to have those values in there so we can roll things up easily. So you can say, how many orders do we make by day of the week? You can now do that much more easily with this date dimension. As anyone who's tried to make these queries with operational data, like if you take the data right out of the the sales system or the order system, and it's all, and you probably have to join like 7-8 tables together just to get the facts you need, and then you give it to somebody, and then they're like, well, can you aggregate this by day of the week? And then you just shoot your hands up and say, oh, I can't. How the heck am I going to do that? And now you're starting to see the value of dimensional models. We're taking the data we already have and we're transforming it so that we can query it in a variety of purposes easily. And one of the key factors in doing that is having a date dimension like this. So this is a conformed dimension. Any place where you would need a date, you would just use this table to do that as the dimension. If I had, for example, an order date, I might, take my date dimension and then make a view called order date dimension. And then if for shipping dates, I might have another view called shipping dimension, and that would just be a view on the same date dimension table. And then when I have employee hire date, that might be employee hire dimension, and that would be on another view on the date dimension. There's no reason to make copies of the tables unless I need to obviously increase performance somehow. But irregardless of the rationale, the point is that you want to have one master place where you keep all the dates in your date dimension. Okay. This is also useful for like every company has a way that they segment out their year. Like, they have their fiscal year and their fiscal quarters. And in the academic world, we have the fall semester and the spring semester and the summer semester. And it's nice because I could take any given date key and then roll that up to what semester it belongs in. And so that's pretty useful. And again, all businesses have this kind of stuff with their date data. Let's talk about degenerate dimensions. So these are dimensions that are actually inside your fact table, and they're there. We store the dimension in the fact table because there's way too many of them for them to have their own dimension. This is usually something like the order number for an order, or this might be the flight number on an airline ticket. This could also be like a particular transaction ID. And so we want to just put those values in the fact table. They're not necessarily facts, they're dimensions, but it certainly, for example, if you have 10 million facts, and each one of those facts and they're all orders, and each one has a different order number, then it doesn't make sense to make an order dimension table that has 10,000 rows in it just to represent those order numbers. So that's what a degenerate dimension is. Again, it's just the columns that we put in our fact table because it doesn't make sense to put them in their own dimension. Let's talk a bit about what happens when the data in the dimension changes over time. This is something that you need to think about because the nature of the dimensional model is that it's going to store data over time. Maybe you have these customers and orders, and the orders are constantly, every month, they're being added to your enterprise data warehouse, or maybe every day, I don't know, or maybe every minute. And what happens when a customer changes their address? How do you deal with that? Well, it depends. There's 4 approaches. We're going to talk about each of these approaches in the next slides. So I'm not going to bother to explain the rest of this slide. I'm just going to jump into it. The first type of change that we can make is called the type 1. This is the simplest form. It's the overwrite rule. What you do is you take that dimension value and you just replace it with the new values. This is appropriate if you have a mistake or an error or any situation where you do not care that you're rewriting history and the old value has no significance. But if the previous value does matter, then you cannot and you should not use this strategy. Okay, as this will cause problems with data that was aggregated with old values. For example, let's suppose you have, we'll go back to a sales data mart, and you have a customer dimension, and you roll up total number of orders, a count of orders by customer name, and you look up me, and you see Mike Fudge, and I made 200 orders, and then I change my name to Bob Fudge, and I keep buying stuff, and then you run the same query 2 months later, and now all the stuff is associated with Bob Fudge, and it's not associated with Mike Fudge anymore. And so you lost all that historical data when I was Bob Fudge. If you care about keeping that change, then you can't use this technique. You have to use the type 2 technique. In the type 2 technique, what we do, this is the most popular strategy because it preserves history, is we take the natural key in the dimension, that is what we recognize as unique about the row in the dimension, and we repeat that, and we replace the old and new values with their, and then we set the effective dates, and we set an indicator row. For example, I have stapler red in there, and then I have it in there 3 times, and one time it was an accessory, and then the next time it was a supply, and then the third time it's an office supply. So I've changed the category of the red stapler 3 times. And if you query this data, and you're asking for data between 4/7/2010 and 9/1/2011, it will treat that red stapler as an accessory. If you ask for it between the other dates, it will treat it as a office supply or a supply, and if you do anything from And if you query anything from April 1st, 2013 forward, it will treat it as an office supply. And you might be saying, well, Mike, do I have to do like select wheres on effective date and stuff like that? And the answer to that is simply no, because you got to remember the facts are being written to the fact table. When you write facts to the fact table, you don't delete those or edit those ever. So from a historical standpoint, if I go back in time and query the red stapler, from April 7th, 2010 to September 1st, 2011, it's going to use product key 11981. If I query today's red stapler, it's going to use the product key 45393. So that's handled for me. The purpose of keeping the different dimensions in there is so that you have a capture over time of how things were, which is important when you're trying to do record keeping. Maybe somebody wants to track the effectiveness of sales of red staplers based on the fact that we changed their category from accessories to supplies. The only way you're going to be able to do that is if you keep track of what it was like when it was accessories. Again, most of the time when you're dealing with changing dimensions, this is the strategy you want to take. Another strategy that we can adopt is called the add new column, which is type 3. So what we do here, this is used not as frequently, but we usually do this when we want to make soft changes. The new value is written to the column, and the old value is stored in a different column. And that way, the only problem with this is we have to rewrite our queries so that they know about the other attribute. This is useful for when you have cutovers of dimensions. For example, you're redistricting sales territories, or you're recharting your account codes. And there's going to be some point when you're not going to use that old accounting system anymore, so you're not going to need those values. But there is a point in time when you have the old accounting system and the new accounting system, and you need to be able to query that dimensional model using both of those codes, so you'll keep them in there. Another way that you can handle slowly changing dimensions is with a mini dimension. Okay. And so what you would do here is you have your fact table, and you have your basic customer dimension, and then you take the things that seem to be changing all the time, and you remove those and put them in their own dimension. This is useful when you're rolling up for example, customers into demographics. So, what gender, or what is your income band, or what is your age band. The data in the demographics dimension changes a lot more than the data in the customer dimension. So for performance reasons, what we do is we separate those dimensions out, even though ideally you would want the customer dimension and the demographics dimension to be in the same physical table so that you can just say customer and see all these things about the customer. It makes sense from a performance standpoint not to do that, so that the things that change more frequently, which are like, you go up in age, or, you go up in income, those things seem to change more often for that particular customer. Those things are in a separate table and not affecting all these frequent changes that are happening to the base customer dimension. Sometimes the same dimension that we have plays more than one role. And a good example of this are your conformed dimensions. They tend to do this, right? But this also can happen where the one dimension table is in the same data mart more than once. For example, you might have an address, like you have you're doing an e-commerce database, you have orders, and the order needs a ship to address and a bill to address. That address dimension is going to be the same dimension, but it's going to be you're going to need it twice in that dimensional model, once for ship to and once for bill to. Same thing happens with airports and airplanes. You have it has an arrival and a departure, and so those are two different dimensions that are accessed in that data mart. So sometimes we have some categories and flags and things like that, and what we don't want to do is make a dimension with just like one attribute in it. It just doesn't make a lot of sense. So what we'll do is we'll combine all of these attributes into their own junk dimension, and this is something that you can write a program to do for you. is because in adjunct dimension, what you want to do is you want to make a row for each combination of the values in all the attributes of the adjunct dimension. So, for example, maybe I have two payment terms, net 10 and net 15. I have three order modes, web, fax, and phone, and I have two ship modes, air and freight. I would enumerate all those possibilities into adjunct dimension. So, invoice indicator 3 is net 10, fax, freight. Invoice indicator 4 is net 10, fax, air. And I would just keep going till I exhaust all the populations, put them into one fixed dimension, and then that way I have a nice, neat way I can categorize my data by, whether it was shipped via air or ordered via fax or sent payment terms net 10 or net 15. I could do all that still, and I don't have to have too many extraneous dimension tables. Another thing that we like to do with our star schema is snowflake it. And what snowflaking means is where you have a dimension that connects to another dimension. And this happens when we have a dimension that is really swallowing up another dimension, and as such, we greatly have a lot of redundant rows in that dimension table. And what happens is when they change, it can introduce a lot of changes that need to happen in the rows in the dimension table. And so here's an example that I have, and I could probably explain it better just through the example. So you have a product dimension, and it has a product name. And normally you might put the size of the product in the product dimension, and the fee that we charge based on the size in the product dimension. You would normally do that. But then if the size or the fee changes, you're going to unnecessarily change several products in the product dimension as a result of that. So again, one of the things we want to try to avoid is changing too many of our dimensions. The rows in our dimension table. Yeah, we have a strategy for changing our dimensions, but we don't want to change too many of those because it can introduce some performance problems. So one thing we'll do is we'll snowflake that out so that the sizes are in their own dimension and they connect to the product, and then we're not changing too many values, we're just changing that foreign key instead. Okay. The disadvantage, of course, is that you are normalizing this data a little more, and it's a little more complicated for users to understand. It's a little decreased performance. These outrigger dimensions are exceptions and not the rule. So you really shouldn't, try to normalize your star into a snowflake. It's not really advisable to do that. You really have to think of the business case for doing that. Sometimes we have a unique situation, where there is a many-to-many, not a one-to-many, between the fact and the dimension, and we need to have a bridge table between the fact and the dimension. And generally, when this happens, we only should do this when it's absolutely necessary, because it is another performance issue. And one of the reasons we need to do this is just like I said, you have a fact and then you have some dimension, and then a great example of this is maybe you have a fact table for medical billing, and then you have a dimension called diagnosis, right? And you all know that you can go to the doctor, be billed, and you can have many diagnoses. Maybe you have a cold and you also have strep throat, or maybe you have the flu and you have strep throat, so you have more than one problem. And so you have to keep a bridge table that associates both of those ailments that you had when you made on that one visit with that one row in that fact table. So this has to happen here and there, but you should only adopt a strategy when it's absolutely necessary. Same thing happens with multi-value dimension. So I just kind of explained this exact same example. But one thing to mention here is that you generally will put a weighing factor, which is an attribute that goes in your bridge table that is somewhere between 0 and 1. And it should always add up to 1. And that way you can take your fact and still make it additive. And I'll give you an example of that. So let's suppose your doctor bill is $100 and you got diagnosed with two things, the flu and a broken arm. So for each of those diagnoses in your bridge table, you would have to weight them accordingly. Like maybe the flu gets 0.7 and then the broken arm gets 0.3. And that way when you go to roll up a bill amount by by the actual diagnosis. You can say, well, that broken arm that Mike got, that's $30. The flu that Mike got, that's $70, because you're taking that 0.7 and you're multiplying it by $100 for the bill amount. But the weighing factor should always add up to 1. This generally ends up being a political issue. You have to get a bunch of people in the room and decide what's more important than which when you go to do this kind of thing. The simplest way to do it is to just divide them all up. So if there's 5 diagnoses, then you say 1 divided by 5, and everybody gets the same weighing factor. But there are situations where organizations do want to put a lot of thought into these weighing factors, because they do get rolled up into actual quantities and values that get used in calculations that make business decisions. So you might have a rationale for making one more important than the other. So there's 3 fact table grains that when you build out a fact tables are based on business rules. And so when you're building out any given fact table, there's 3 ways that you can, there's 3 basic behaviors of that fact table. There's transaction, periodic snapshot, and accumulating snapshot. So the transaction fact is the really kind of the most simplest form of fact table. You get 1 row per transaction. So think about this. You go to Target and you buy a pack of pencils and a DVD movie. And so each thing that you buy from Target is a transaction. So the pencils, 1 row in the fact table, the DVD, another row in the fact table. So generally the transactions correspond to a point in space and time. Once they get added, you do not go back and delete them or change them. They're static, and again, they occur over time. And when they're inserted in the transaction, when the transaction occurs, they get inserted into the fact table. Now, there's a couple ways that this happens with ETL. In real time data warehousing, as the transaction occurs, a trigger would also occur that would transform that transaction into the fact table. But also, you can do this on a batch, so like every day or every week or on any given time interval, you revisit the transactions that you have in your operational system, and then you transform those into the fact table. So this can be, examples of transaction facts are sales, the sales process, the returns process, telemarketing, event registration. These are all transaction facts. There's also a type of fact table called a periodic snapshot, and this is a little different than a transaction fact table. What happens is each row in the fact table corresponds to an interval of time. So the level of details are stacked in the fact table. Generally, the interval of time is done at some granular time period that you care about. Maybe it's every 5 seconds, maybe it's every month, every week, every hour. This can serve as a nice summary to a transaction fact table, but it doesn't necessarily replace a transaction fact table. An example of this might be a financial report or bank account values, class schedules in a semester, when people log into the labs, that kind of stuff. There's also something called an accumulating snapshot fact. This is used This is not used as often, but it suits a very specific need. Generally, when you have a business process that involves a series of time-stamped workflows, you need this type of snapshot fact. And the other thing I'll mention about this is that this is really the only fact table that gets updated. All the other fact tables, you merely insert the data in the rows and that's it. You never touch it again unless you made some mistake. The accumulating snapshot, you start by adding the row, then you continually update it as the workflow continues. Then when the workflow is complete, you no longer update the row. And generally speaking, this fact table has a lot of dates in it. So a good example of this might be fulfilling an order. You go from order fulfillment, shipping, did it arrive at the customer, applicant tracking job applicants, like they applied, we called them, they were interviewed, we interviewed them again, we made them an offer, they accepted the offer. So you're tracking that process from step to step. Well, one important rule to recognize here is that your fact table cannot have different levels of granularity. When you look at your fact table and you look at the row in the fact table, that means something, and you should not change that meaning based on the individual facts. So, for example, if you have an orders fact table and you have quantity in there, then that quantity should be for a particular item on the order. You shouldn't have another column in there that represents the total quantity across all the items on the order. Those are different grains in the fact table. You want to do that. If you need to do that, then you should create two separate fact tables, one for the items on the order, that would be like a transaction fact table, and then one for the full order itself, that would be, some kind of that would be another transaction fact table at a different grain. There are also factless fact tables. These are business processes that do not generate any quantifiable measurements other than maybe counts. And a good example of this is taking attendance, or the admissions process at a college, also maybe job applicants. This tends to kind of go hand in hand with the accumulating snapshot. One useful thing to consider is you might have a fact table and then another fact table, and you want to take the facts in each of those fact table and kind of use them or compare them to each other, and that ends up being not easy to do because these fact tables end up being enormous. So sometimes we'll do what's called a consolidated fact table, which is we recognize this situation exists, we combine both of the individual fact tables into one fact table, and then that way we can then compute the value that we need in that new fact table. This is called a consolidated fact table. You might have two different data marts, like a sales data mart and a forecasting data mart, but they in essence use the same fact table, and you do this mainly for performance purposes. So I'd like to leave you with some do's and don'ts. I mean, there was a lot of things that we covered today. Let me just sum it up by saying when you go to do some dimensional design, don't take a look at reports, or don't take a report-centric approach. Think of what problems your users need to solve. Don't look at the existing reports that you have and try to build dimensional models from them. Dimensional models should not be departmentally bound. You need to think about the entire organization, not just the needs of the individual group or department that you're working with. When you create your dimensional models, use the finest level of granularity possible. You can always roll those up into a summary fact table later on if needed. But if you capture your data at the highest level of granularity possible, you're going to have the most flexible and scalable solution. And then where possible, use your conformed dimensions. That's going to help with integrating one particular data mart with another particular data mart that you have. So if you have one departmental need and another departmental need, you'll be able to kind of combine and reuse a lot of what you've done by using conformed dimensions. I know that was long, but I knew that was going to be long. That kind of sums up dimensional modeling. In the next lesson, we'll talk about the approach that we take to designing the dimensional model. Now that we understand the terminologies and we understand the importance of how to do all this, we're going to talk about the process that we follow in order to capture this information that we need to create these dimensional models and then document it so that we can then go ahead and do it at a later date and time. All right, sounds like fun. We'll see you soon. Thanks a lot. Bye now.